Hey everyone, hope everyone is doing well. Welcome to today's video on systems of equations. Now let me just start with a quick refresher on what a systems of equations problem looks like. So we're typically going to get two equations. I'm just going to write them down here. Negative 1/3 x plus y equals, let's say, positive 1. So like I said, there's two equations, and we're typically going to have two unknown variables. So that's going to be an unknown x variable and unknown y variable. And it's a pretty straightforward way to solve it. All we have to do is figure out what the x value is and what the y value is that makes this equation true. So as I highlighted here, there's three ways that we solve these kinds of problems. There's substitution, elimination, and graphing. For the purpose of the ACT, I really don't recommend graphing because it's pretty time consuming, but it is a valid method to solve it, so let me just go over that one first really quickly. This one's graphing. And let me just use the same example that I used before. The one with minus 10, negative 1/3 x plus y equals 1. So how do we solve this one? We basically just graph these two equations and see where the intersection is. So let me just go ahead and do that. I'm going to convert both equations into slope-intercept form. So the first one right here, we're going to do y equals 4x minus 10. Second one is y equals 1/3 x plus 1. And let me just rewrite it here so we don't forget it. Y equals 4x minus 10, y equals 1/3 x plus 1. And I'm going to graph it in this crude graph that I just made. The first one, let's see, start with the y-intercept, negative 10. Slope of 4 would look something like this. Okay, second one, y-intercept of 1, a slope of 1/3, positive 1/3. Look, I don't know, something like that. So this point over here is our solution. And this point over here is, you can't really see it because I drew it pretty badly, but spoiler alert, it's 3, 2. So x equals 3, y equals 2. That's the solution for this particular problem. But like I said before, on the ACT, I really wouldn't recommend drawing out a graph every time because there are simpler ways to solve it. One of them being elimination. This one is a personal favorite of mine. So with elimination, actually let me start by writing out the problem. We're going to use negative 3x plus 7y equals negative 16, negative 9x plus 5y equals 16. So we're trying to find the x and y values of this problem. In order to do this, we want to try to eliminate one of the variables, either the x or the y. And we're going to try to multiply this equation in such a way that we can do that. So right now, I'm aiming to eliminate the x variable, but my coefficients on the x, they're not similar. We have a negative 3 and a negative 9. So what I'm going to do is I'm going to multiply this first equation by negative 3 and rewrite it on the bottom. So that's going to be, when I multiply the whole thing, it's positive 9x minus 21y equals positive 48. And then I'm just going to rewrite this equation over here. Negative 9x plus 5y equals 16. So I've multiplied this in a way that my coefficients for my x's are now positive 9 and negative 9. So if I add these equations together, I found a way to cancel out the x's because positive 9x plus negative 9x is just 0. So I can go ahead and add the rest of this problem. So negative 21y plus 5y equals negative 16y. 48 plus 16 is 64. With our with our division skills, we can figure out that y equals -4. But we're not done because we still have to figure out what the x value is. From here, it's pretty simple. It's just a good case of plugging and chugging out an answer. So I'm going to pick this first equation to plug it into right here so we can find out our x variable. So we know that y equals -4, and we had our original equation, -3x plus 7y equals -16. I'm plugging this into the y right here. So I get this plus, let's do 7, -4 equals -16, which is the same thing as -3x minus 28 equals -16. That's -3x equals, we add 28 on both sides, that's some plain old algebra, and we're going to get equals 12, and x equals -4. So the solution to this problem is -4, -4, because both of the x and y values are -4. So that was pretty simple. But another way that we can solve systems of equations is through substitution. And I'm going to write a problem down. I'm going to write -5x plus y equals -2, -3x plus 6y equals -12. Now the way we handle substitution problems is we're going to solve for one variable, and we're not going to get a value, we're just going to get some sort of solution for that variable. And we're going to substitute that solution in to find out what the actual values of the variables are. And let me just show you what I mean by that. So right here, I'm looking at this y over here. I'm trying to isolate this y. So this particular equation right over here, I'm going to rewrite it as y equals 5x minus 2. All I've done is brought this 5x over to this side. So I have some type of solution for y right over here. I'm going to plug this solution in to this second equation and this y over here, because we already figured out that y equals 5x minus 2, so we can plug in 5x minus 2 for any y that we see in our second equation. It's getting kind of messy here, so let me just start a new page. The second equation I was referring to is -3x plus 6y equals -12. We found that y equals 5x minus 2 based on our first equation, and we're just going to substitute that in. Plus 6, so substitute that in for y equals -12. That's -3x, do some distribution. Minus 12 equals -12. This simplifies to 27x. Add 12 on both sides equals 0. So our x equals 0. Same thing as we did with elimination. Now that we have one variable, we can just plug that in to one of our equations from before. So let's see, we have x equals 0, and I'm going to plug this in to our first equation. First equation was -5x plus y equals 2. We found out that x equals 0. So another good case of plug and chug. 0 plus y equals 2. 0 plus y equals, oh, I'm sorry, that was -2. And then y equals -2. So our solution for this systems of equations problem is 0, -2. And there's something I just want to point out. In this problem right over here, it was really simple to get this y solution. As you can see, all we had to do was move this over to this side. We didn't have to do any division or multiplication to get a solution for y. So you'll find out that in these types of cases, substitution is easier to do than elimination. And that's something that I really want you guys to keep in mind when you're practicing these types of problems, because for purposes of the ACT, you want to be able to do the problem in the easiest, fastest way. So you'll find that in some cases, substitution is easier to do than elimination, and in other cases, it's easier to eliminate than to substitute. So keep that in mind when you're practicing those